Yes. There we go. And we're live. Okay, hello everyone. Have you survived your midterms? You still have more to go. How's the morale in the room right now? Are we doing good still? Or yeah, I just finished one, so I'm a little bit tired. Yeah, so maybe the energy on this meeting will be a little bit lower, but we're just gonna chill out and learn some cool data science. So yeah, so remember that next week our guest speaker, our Lord and Savior Travis DeSell, will be coming, and then his talk will lead into his data set that we're going to use for a hackathon / data fest. So we'll give you guys an actual data set from his company, and you'll be able to like deal with it for a week, and then we'll probably have you guys present some of your results and what you find, because we want to give you guys real world experience on like real world business data. So start finding a group for that. Probably groups of like 2 to 4 would be good, unless you want to solo it, I suppose. No one's going to stop you. So today we're doing data cleaning and feature engineering. So we're done with our kind of basic tutorials. Now we're getting into, okay, we're going into the heart of data science. And when I mean the heart of data science, I'm not joking, because if you look at this plot, it's pretty representative of the actual workflow of a data scientist. And if you see the most or the biggest slice of this is cleaning and organizing data. So everyone likes, the sexy machine learning models and all the statistical analysis, but really as a data scientist, you spend 60 to 80% of your time just dealing with data. How do you actually make the data usable? How do you clean it? How do you organize it? How do you engineer new features off of it? So if you're really set on being a data scientist, just make sure you like wrangling data. If not, you can look into like, solutions architect things, or maybe machine learning engineer. But as data scientists, that's what you're in. You're in the pits. You're in the trenches with this data. So we're going to go over how to actually clean and feature engineer. So let's look at a data set that I created to intentionally be dirty. So what things do you notice about this data? Like, why is this not ideal? Go ahead.
The height. The first value says NAM.
Yeah. So there's missing values. What else?
Like that.
Yeah. So with the date of birth and also with the height, because let's say people are actually, inputting this data, they're inputting it in a very human way, but not in maybe like a data science way. So like, especially with the height, like 6'1", that's not a value you could just like plug into a model. You're going to break something, because now that's a string. That's not an actual like integer value or float. Same thing with the date of birth. It's all hyphenated, month, year. And if you look, someone has misinputted data, as you saw correctly, they just typed 9 one too many times. But if you're thinking like this is like medical data, and like you're a nurse or a doctor or something, and you're just kind of like, putting stuff in, there's going to be errors. And I've seen data sets that are as bad as this or worse, where you get it from usually some industry where they're not thinking about data collection. They're like, oh yeah, we kind of just collected this data. Can you do something with it? I'm like, this is the most terrible thing you've ever like given me. I don't know why. Like, why do you hate me? So yeah, I pointed out everything that's bad in this data. So we're going to learn how to deal with it, because you're going to encounter this in the real world. Not everyone's actually doing like quality data gathering. So what's the first thing we can do? So the first thing we can do is data imputation, which data imputation is filling in missing values. So a lot of times you do this with some sort of statistic, like the mean, the median, or the mode of the data. But for this, I didn't think it would make sense. Like, we don't know this person's height, but taking the like mean height also wouldn't make sense. Same thing with the weight, because it's not like these are independent people. You can't really like, extrapolate off of other people. So I decided to be a little bit smarter and go to an actual like BMI chart, because we have some broader population statistics on how much people like weigh versus their height, and how much people or how tall people are based off their weight. So we can go out and look at other sources of data to fill in our missing blanks as well, not just use statistics within it. Yes.
One thing that people do with height I've seen is like they'll convert it into like inches. So like
Spoilers. Yeah. Calm down. Jesus. Like, so yeah. And one thing we need to do is we need to parse the data, right? Because it's in this, hyphenated format that's completely junk on the programming level. So a really common tool we use in Python is it just has a split on any type of like string. So for here, I can parse the dates into month, day, year just by splitting on the hyphen. Now the height is a little bit more of a pain in the ass because it's like, multiple like regex symbols that we don't like, but I simply just did splitting twice. So once I split on like the inch or the foot, and then I split on the inch, and I split off the regex and then took the elements that were actually numbers. And we also need to do a little bit of spot checking, right? Because we had that one value that's like, in the future, as you said, so someone just misinputted the date. So we just got a spot check. So I'm just checking if the year is like actually a length of 4. And when you spot check, you can either just raise a flag, say, hey, if the data doesn't look like what I want to look like, just tell me. Or you could just remove that row because you're like, I don't want to deal with this. Somebody misinputted this. This is not my problem. Bye. Or you could replace the value. So for me, what I did with this was I simply removed that last number if it's greater than a length of 4. And then finally, encoding, like as Tolu was saying, you can turn like the height into inches, or you could turn into like feet, point, like inches, right? So it's a way better way of dealing with it than dealing with feet and inches if you don't want them as separate columns. For the date time, like the month, date, year, there is a date time object that Python has, which is specifically meant to deal with this. And the date time object has a lot of cool tools in it to actually deal with date time. What I used was there's a date time encoder that turns a date into a string of numbers. There's different encoders you can use, like you use like Gregorian date. You can just like convert it into like seconds from like New Year midnight. I don't remember which one is the yeah. I don't remember which one this encoders is. Yeah. But it encodes my time into some number that I can then decode later, but now it makes it into an actual like usable feature to me. And then for further encoding, we can like one-hot encode or just binary encode the person's sex. So like male can be 0, female can be 1, and now we took it from a categorical string to an actual number. So now we have cleaned up this data much better than it was looking. So now we filled in our missing values and we got everything into actual like usable information on the coding side of it. So everything's the same data type and we filled in, all the information that we need. So now the data is clean, we can go on to feature engineering. So what is feature engineering? We took this big long quote out of our textbook, but last time I found I can't present and read at the same time, so you can read that. I put a little summary line for myself on the bottom. I would say that feature engineering is creating new meaningful features with the features we already have. So how do we take the information in our data and go further with it? So with our data, there's a very like intuitive thing we can use. We can use the BMI, which BMI is just weight divided by your height squared. And because we're using America units, we need to scale it because BMI is because BMI is defined in metric. But if you use feet and inches, there's like this scale factor here. It's actually, this just converts it over. And also from so now we have a new column, BMI. But also from BMI, you can take the actual medical like rating of someone. So someone can be underweight, healthy, or overweight, and you can tell that from their BMI. So now we've taken 2 features and we've made 2 more of them. So now we have this BMI feature and this class feature, but we need to look at how we have highly correlated features now because we literally used their height and their weight to get BMI. So now we have like redundant information, right? Because if you have BMI, then you can capture the information of height and weight. But what I would argue is that you should keep at least one of them, because if you have either height or weight and you have their BMI, then you can, find the other one. But if we remove both these columns, then we've actually removed that information. Because if you start at BMI and you only have it, you can find the ratio between the person's height and weight, but you can't actually find their height and weight. So I'm choosing to keep one. So now we've cleaned and we've engineered our data set to get more information out of it. It's all in a usable format. And now we have more insightful information to work with. So we're trying to like classify people further or like, predict some outside thing. Yes.
So in general, if we have any features that we're using and attributes that we're turning into one feature,
Mhm.
we use it in minus one.
Not always. It depends on your problem. Like there is this thing called principal component analysis, which is looking at how your features are correlated. So you can remove some to like get down to a feature space that is like simpler, which could make things more easy to classify. And that's usually like feature 1 and feature 2 are super highly correlated. So you only need one of them. I would say it's context dependent. Like in this case, both height and weight are both correlated to BMI. So I could take out both of them and still keep that information, at least in some form. But I decided to keep one feature because you can't back extract these single features out of our created column or created row or column. And yeah.
So I noticed that you said that if you were you're reducing the BMI, you can calculate whether someone is overweight, underweight, things like that.
That comes from that's from like medical science. They have designations based on in their field. So now we're reaching out into the medical field and saying, how do you classify people? And we're adding that information in because now we have the BMI.
So it's using domain knowledge. essentially.
Yes.
So generally you would want to talk to a specialist in the area in which you're doing this to try and help you identify attributes and classify them based on what they know about the domain. If you're not knowledgeable about
Yeah, because if we only had BMI, we couldn't generate these classes because we're not in the medical field. But I went out and said, hey, I have BMI. What other information do you guys get out of it? And they're like, okay, they classify people as like underweight, normal, overweight.
So the question is that if we create a feature like BMI, and let's say it's not necessarily correlated with being healthy or unhealthy,
Mhm.
would the model be able to sort of fix that, or is that something that we have to like do?
It depends on what you're trying to model. Like you're trying to model like how healthy someone is, which because class comes from BMI, these are like directly like binned together. I don't think that a model doing that would be too like insightful. But if you were trying to answer another question, like let's say we had a label over here, like we were trying to figure out life expectancy. Let's say we have all this information and we want to figure out how long someone might live. Then I would say that having BMI and class could be useful because if even though you have BMI and it puts them in a certain class, having them classified that way could, give you better accuracy with that prediction.
And the reason why I bring this up is because the BMI is not necessary. So the
Yeah.
BMI can't tell if someone is like muscular
Or yes, that's true. And so someone who's like considered overweight because they're like, Arnold Schwarzenegger, right? Like, and so that's a time where the BMI wouldn't necessarily correlate to life expectancy because he's probably going to live a long time because he's super strong. Yeah.
It gives something to start with.
Yeah. And so, yeah, this is the last slide for this, just kind of taking you through a general process with like a completely just dirty data set to something that's like highly usable. Does anyone have any questions or is it clear how I did this? Yes.
Isn't the good practice to like always keep dropping the column, right? That means like we are just like reducing the features which might lead to like not.
Well, sometimes you want to reduce your feature space. Yes, sometimes, but I would agree before you start your problem and you're just taking an initial stab at it, probably keep everything to see what's actually useful, right? Yeah. I just wanted to put an example here. When you make new information, sometimes it's like you can get redundancies that you might need to take care of. Like if you were to, let's say, do like a some type of regression fit with this data and you kept like everything, then like maybe one of your coefficients on that is going to go to zero because it's not using that information at all because it's captured in another feature. So you could reduce the complexity of your model and keep it just as accurate by removing a feature. And that's just better for efficiency.
Sweet.
Again.
Sorry, after the BMI, I just wanted to go over how did we get height. So we took the weight, we went through the BMI first, and then
Yeah, so like how we did our data imputation. So a BMI chart is plotted as a height versus a weight. So it's if you are this tall, how much should you weigh on average? Or if you're, at this weight, what should your height be on average? So this is all made from just population stuff.
what is the formula of mine?
Yeah, there is like we use the
It
formula.
was weight divided by square.
Yeah, and in metric, you don't need that, scale factor, but yeah. Yeah, we discussed that. It's just like an example, like I'm showing you how to get more information, like, yeah, but obviously we can get into this more and there's, other things we could, engineer, like we could just turn like date of birth into just age, right? And in their current age, and then have that as a feature and just remove date of birth or something, but
Just a heads up, having current age is a bad idea.
yeah, because that means your data set's frozen in time. Especially if you remove the date of birth and only keep their age, then it's, yeah.
And unless your data is like updated almost daily, having current age does not work well.
Well, sometimes it depends on the okay, all this is context dependent. Sometimes you want it frozen in time because if you have like when like people, let's say, first get like a cancer diagnosis, maybe you want the average age where that happens, not necessarily their birthday. Yeah, snapshot.
That's not current age.
Yes.
Look,
That's
the
the
time of-
at the time of you want to record their age. Yeah.
Sometimes the date you can like derive like day of week feature or something like that. Those
Yeah.
are very useful, especially if you are doing something with analytical. Like on weekends, some sales would be higher than like weekdays. So that's a very important feature we do
Yeah.
with dates.
It's another example. Do you want to go into the tutorial now? Are we good on the conceptual level of what we're doing? Yeah, okay, I'll hand over to Tolu then.
Sweet. All right, how's everyone doing? Good. Good. So what I'll do right now is just post some of the information inside the Slack channel so that we can just have it publicly available. It's going to be posted on the GitHub once again, but of course, just for the sake of you guys having access to it right now, tutorials, engineering this, I worked on this morning. through the afternoon. And I think housing CSV is at it. Yes, it is. Carry over, please. Okay, thank you. I don't remember, to be honest with you, but you will see shortly and things will be good. Okay, I need to open Jupyter Notebook. It seems. Oh no, it's open here. Okay, never, just kidding. All right, so here we go. Yeah, full screen. Alrighty, so
No, it's fine. It's fine.
you guys all see it? All right, cool. So yeah, like we said, do some feature engineering. So yeah, welcome back. This is week 4. We're going strong, and so here we go. So why do we choose? So I chose to use a housing data set. I think one of the most basic data sets that you'll ever run into, apart from like the iris, like flowers, is actually I think the Boston housing data set. It's like usually like used for like homework assignments. So I was like, if you guys have seen it already, this will be familiar. And if you haven't seen it, this can be helpful to you because, your homework, you're going to be like, oh, how do I analyze housing data? Well, Data Science and Engineering Club, which meets Thursdays at 5:30, 6:45, and GS and GCI 1720 went over it. So this is a good example. Yeah. And so this is just a cute little infographic, just to say, in the context of feature engineering, you want to take a couple of features and maybe either combine some of them to make a more condensed feature that captures information or generally speaking, you just want to reduce your feature space to remove some clutter in your algorithm altogether. So here we go. And so first things first, of course, we always import our libraries. But also, I got some of this information from some guy named Alexander Hagman. I don't want to claim that all this is exclusively my work. Plagiarism is bad, so got some assistance from him. So yeah, first things first, we of course upload or import all our libraries, in which case these are the ones we talked about: Pandas, Matplotlib, NumPy, Seaborn, and a few others. This is us reading in the data. df underscore, yeah, so was it? Yeah, df is what I called it. And we're just literally like reading in the housing CSV data. And so here I'm just quickly writing in some of the relevant features that we have. Longitude and latitude, there's housing median age, there's total rooms, and you guys can read the rest. One thing I will say is, like, when I was doing this, I found that there's some like really robust like housing data sets. Like if you're going to predict the value of a house, for example, one thing you might want to consider is like, and this is like a spoiler for what's to come, but if you have like a waterfront property, like apparently living near the beach raises a house's value by like a tremendous amount, despite tsunamis and, you know, potential, yeah, despite global warming and like potential, you know, natural disasters. But you could also look into like these robust data sets that have things that you might not even remotely think about, some of which include air quality. Some like cities and regions have like incredible air quality, and that actually factors into the price of the real estate market. Neighborhood crime actually contributes to some real estate housing prices. And also there's something called noise pollution. I've heard of this before, but actually there are little communities in the United States where you can measure the decibels of like traffic in an area, and that literally has like implications on the predictive power of what a house will cost. I thought that was like colorful. I thought that was neat. And so these are just the features that we're working with, but certainly there's a lot more if you work with other data sets. So first things first, let's see what some of our data looks like. Again, these are our columns, our feature headers. So I want to see how much rows and columns we have. So it turns out we have 20,640 rows and 10 unique features. Of course, these are them. And so we'll keep going. So we want to read in some of the information that we have. You know, what are the data types? Are they null? And so we have all of these are floats, with the exception of ocean proximity, which I just mentioned to you guys. How close you live to like a large body of water can often influence the price of a house. So this is us doing, like we said, df describe. We want to take some basic elementary statistics on our data set. And so these are some of them. You'll notice that the median housing value really does like change quite a bit with respect to percentile, the mean, standard deviation, and the housing median age will have like standard deviation of 12. The mean is 28, is 28 years old, 28.6 years old is the housing owner. So it's kind of interesting. And these are some other elementary stats you can check into. And so because this one thing, ocean proximity, was an object data type, I just want to like look at it because it just like struck out to me as like interesting. And so I looked at df describe include O. So this is just include is like one of the various little sub features you can look into inside this describe method. And I'm trying to read in specifically what it did. I remembered when I was doing it. Yeah, it just looks at, I think, categorical information. So this is just telling us ocean proximity. We have five properties that are near the ocean. And this means, or at least I interpret that to mean, it's less than 1 hour away from the ocean in particular in this data set. And so that's just some more information. So I continued looking into it. I said, hey, I want to know what the individual pieces of information are in ocean proximity. So you have houses that are 1 hour, less than 1 hour away from the ocean. You have houses that are like inland. By the way, this data set is in California, just so you guys know. So it's a coastal part of the United States. And so there's some houses 1 hour away from, less than an hour away from the ocean. Some are inland, some are just near the ocean. Some are near the bay, and we have island-oriented housing. So moving forward, I wanted to see if we could just check out some stuff on the total bedrooms. And so I just looked up the value counts, but I didn't really even understand fully how to interpret this. So I didn't know if this was too helpful, at least, or maybe I wasn't interpreting it the right way, but you know, it's something we can continue to look into over the course of this. So this is just me saying, hey, let me look at some of the numerical features using a histogram. And this is just some of the information we got. You know, we looked at the longitude, and it gives us like certain counts with respect to latitude. This is with respect to all of our our features, except for the ocean proximity, because that wasn't a numerical value. So now we get into some of the data cleaning and feature engineering. So like we said, data cleaning is getting rid of like NA or NAN values. Maybe you want to perform some data imputation like we did with Lee in the context of the BMI. Or maybe you want to just like remove things that are just like outright wrong, things that just don't make sense with respect to the given like row or column. So that's what data cleaning is. And so I dropped all the NA values by doing this method, drop NA in place equals true. It means that moving forward through the entire like process of data science that we're going through, we're going to remove all the NA values and it's going to hold. This command is going to like make sure that our data set now moving forward, we dropped all the NAs. Yeah, for sure.
Also, to drop the NA, does that mean to drop all the rows contained in the?
Yes, that's exactly what that means. Yeah.
So then the rows of our data set will be reduced. Yeah, like.
Yeah.
They basically, the idea is you don't use rows as not incomplete data.
Yeah, this is what I chose. In some contexts, you'll maybe take the mean average of that column and you'll just like all the like blank values, you'll put the mean instead. Sometimes we'll put the median in that like those missing values. It really depends on like the data set that you have. In this case, I decided to just like we call it feature engineering. Yeah. we call it feature engineering, my friend.
He's talking about the feature engineering for the sake of implication.
Yeah, you can.
Because if that feature highly correlates with multiple, then you can make some function that describes.
Yeah, like it's not necessarily like take one feature. We can like consider two features and like according to that we can like put in like accurate value.
Yeah, you could use correlative features to get better predictions on missing values, but ideally, like when you have enough data, you can just drop the couple rows because it's better to not use data than to use bad data.
Me too.
That's a cool idea.
Yeah. Yeah.
When you feature engineer, you are creating new columns.
Yes.
There's scenarios for that. I'm also familiar, like there's definitely scenarios where people just take like the average of like a particular like, numerical column in case, let's say you don't have a lot of data. Like in there's scenarios, at least in my understanding, where if you don't have a lot of data, it's better to use imputation than to outright just get rid of rows.
We're talking about using other features to do imputation.
That's the doing information can just for information.
I think you
And
could
not
like.
create a new column.
Yeah, so the idea is you use correlation between related features to identify how they're connected. And based on the correlation found, you use that with features that exist in your rows and as missing columns to get the value of missing column.
Six is fine, but if you are engineering a new feature, this is really the feature, then you can use it.
We're talking about filling in values of one
Like,
feature.
right? Like, yeah, suppose I have a column and I have 10 missing values. And for those particular 10 rows, I have other features that are not missing. So suppose this is my missing value.
Yeah. We're talking about like one column and like it's a numerical column and there's like literal like 4 cells out of like 500 emits. Like you can just like put the mean. It's not like it's not a big deal.
But I think it's a cool idea. Like, let's say you have missing data in a feature, and then you create a model for that feature based off your other features, and then use that. I want to do that.
Okay, well, feature engineering, ladies and gentlemen. So
What I think it does, like if you don't use the request field, you have to store it into another Python variable. But if you use instance field, you don't
it
have to-
holds it. Yeah. Like now the data frame is always going to like have the removed data.
Yeah, but what I'm saying is like, it's like, maybe you don't want to change your whole data set, so like you use another variable to store your.
Oh, I see what you're saying. Okay.
You might need it later.
Well, yeah. I'm a creature of habit. This is what I usually do, but because of you, Sujan, I will keep that in mind. So now let's I want to create a feature. Let's say we want to generate a new feature, for example. And so how are we going to do that? Well, I'm going to create a new column. I'm going to call it rooms per household. And so you might be wondering, how do we create this kind of like feature inside our data set now? So what we would do is say, hey, we have the data frame, we put it in a list comprehension, and well, not a list, just like brackets. And then we would just like name the actual new column that we want. And then we're going to assign it to a value. So in this case, I said, hey, if we have total rooms and we divide it by the households, like we could create rooms per household by doing so. And so that's what I did. And so I took a look into what that variable would produce. And so now we have this feature added to our entire data set. This will probably be added to the end of the entire like data frame. So if we have 10 columns, this will now be the 11th, for example. And so moving forward, I wanted to see, some of the smallest and largest values inside this new column that I generated. So I decided to say, hey, I'm gonna take the smallest and the 10 like smallest values with respect to this column. And so these are them. And then I want to take the 10 largest just to get further inspection on what this data is starting to look like now. And so I used n largest, and I used 10, I took 10 values, and then that's what we see right here. And so now I noticed that I have a couple of like weird looking values here. Like we have 0.8 of a room. I thought that was like particularly strange. So I was like, okay, maybe that's going to be something that I need to look into. And so these are the associated, like, I forget what these are. Divided by what? So I divided the rooms divided by the households. So that would give me like rooms per.
Rooms per household. It depends on the different household. Is a household, the family.
Yeah, that's.
How many separate families do you have in that household?
Yeah.
So many rooms.
Oh.
So I
Having less than one is a very California
It's-
thing.
it's something like you're sharing, like you have like 7 or 8 families.
Oh, shoot. Yeah. Well, it's better than I was closing, so.
Maybe basically you have more families in the rooms.
So that means you have point something of family.
Okay, yeah, I'll be sure to double check the vet a little bit better ahead of the next meeting. This is
Plug it in and-
technical, or maybe not technical, total difficulty for a second, but give me one moment and we will find this out.
Now we figure out like video editing, right? So,
Oh yeah, video editing is not as bad. Sweet. Okay, so moving forward. I just decided to take a look into them, like rooms per household. I don't know if I was interpreting them particularly well, or if they didn't make, or if they made any sense. So I kind of just tried to look into tried to create a new feature set, which was bedrooms per, I should have said per household. Yeah, per households, what I should have written, but you guys I'm sure can pick up. And so I took the total bedrooms divided by the total rooms altogether. And so bedrooms per household would read this column.
That's how many rooms in a household.
Yeah, that's what I was at least aiming for with this. Okay.
So essentially, why are we using there's one.
I mean, it depends on what information you want. So you want
Yeah.
to know like the percentage of this house that consists of bedrooms.
Basically, come down to percentage.
That's what, yeah, I didn't think subtracting would help me in that case. I thought it
That
would be.
just figures out how many.
Or you can say it's even normalizing it by the number of households or rooms or whatever.
So yeah, this was another thing that I tried to like create population per household. I ran it, but I think you guys will get the point of me trying to just create new features based on like these simple calculations I was trying to implement. So now, what are some things that may change the price of a house altogether? So when we're trying to like predict these kind of things, this is what I was saying. If you just take like a general conversation between all of us, you would think maybe, the location of maybe if a house has a garage or a parking lot, maybe if a house has a pool, like these are things that might have an influence on the price of a general house. And generally speaking, depending on the state you live in, there's like different values that can be associated with this in terms of predicting the final like price of this property. So that's kind of like what this segment is going to get into. So again, just reading in the data frame. And now I just want to look into the median house values and just look at like just the general spread of the values. So I'm going to try to actually decrease this a little bit. So these are the values of the house. I think these are the prices of them. And so we see it's capped at 500K. And we see that there's a lot of activity between here. I would say most of the activity is between these values. Yeah.
Because anything past 500K was set to 500.
Yeah. So all the outliers are basically capped. And so now I'm just taking a quick correlation to kind of try to see, like, you know, if we have a housing value, are there any of the other features within this data set that have maybe like a particularly like high correlation with the price of this, to maybe see if there's like some linear relationship between them, in which case median housing value is going to be correlated with itself, which is why it reads 1. Median income was actually, I guess, the highest predictor here. It says that it's like 69% correlated, which means it's pretty like strong, I would say. Pearson correlation coefficient, if you have anything from, I think it was 0.6 to 0.8, it's like pretty strong. Anything above 0.8 is like, all right, like yes, strong correlation. And anything below 0.6 is pretty tenuous. You can't really say. So yeah, these are the values, and I sorted them in descending order. So ascending, I put false, so that it was like from high to low, because it defaults at low to high. And so I want to take a look at the distribution of the median income, because it was one of the things that was highly correlated with the house value. So here we just take a quick look at it. And there we have it. This is right skewed, I believe. Right. I always get mixed up between left and right skewed. Yeah. Yeah, there's like a relationship between left skewed, right skewed. Basically has an implication on the relationship of like the median of the data set and the mean of the data set. I remembered it this morning, but I tried to remember this morning.
Your mean will be dragged towards the table.
Okay. Well, there you have it. It'll be dragged towards the, I really tried to commit that to memory, but onwards. So here I tried to create a scatter plot relationship, or it's called a joint plot actually, using the median income and the median housing value. And so this is just us showing, hey, some kind of linear relationship between these two features. And I would say it's like, there's some linear relationship between them. Again, we see the 500K is like a hard cap for all the housing values. But the spread, I believe, does show a general kind of trend that we can like rely on. And so, yeah. So here was me using a kernel density estimation. I just like the way this looks, honestly, but this will tell us where a lot of the values are coming in. So it seems to me that the median housing values that are like the greatest in terms of like all the houses, we have the greatest amount of them in this region, like the 100, or like I'd say like 70K to like 180K region is like a lot of the density of the houses are there. And then as we start to progress into higher housing value ranges, it becomes lighter and lighter, which means fewer and fewer houses of this price. Long, yeah, definitely not recently. Definitely not recently. But that's how I interpret this. And so this tells us the most frequent income, the most frequent median income is somewhere between values of 2 and 4. And then, yeah, the housing values are roughly 80K to like 180K. So this is also, in my opinion, I believe this is like linearly related. At least it follows like some kind of like linear trend. So that's how I interpret that. So now I wanted to take a different approach. Let's like look into some bubble plots. And so I wanted to take into account the scatter plot. I wanted to use longitude and latitude because these are values that I don't normally see on any data set at all. So I thought this was kind of interesting to look into. I want to look into the population. I want to look into the median housing value. And one of my favorite color maps is the spectral color map. It's a rainbow. It's like the most colorful of them all. So, you know, just decided to fill in these parameters and of course, label the graph with longitude and latitude, and then just see what it produces. So this is the outcome. The larger the dot, the more expensive it was, I believe. So Yeah, this corresponds to no, the bigger the population rather. The bigger the population correspond, yeah. So here we go. We have the latitude here, longitude here. This is the housing value. The colors represent how expensive the house was, how expensive the house was. And so we see like in some of these regions, there's like a large density of different like price ranges, particularly here. And we see more like inland in California, the houses are a little cheaper. Whereas on the coast of California, we see that we have a lot of blue values where you see, you know, as you get more expensive, you become progressively more blue. Little sidebar. I kind of realized that when you're actually analyzing this value and like image value altogether, like images altogether, I decided to get like a California map because I overlaid this data set, this plot on top of the California map itself, which we'll see in a minute. And just a shameless plug, there's a lot of cool like scientific computing you can do with like pictures in general. So all these filters you see on like Snapchat or like these like colorings are actually just like quick little math functions on like the pixel values. So if you actually want to learn about that, you can just click this link. It'll like show you some stuff. It's just a picture of some fish. And these are just like literally just some filters that were overlaid on top of this these pixel values. So I thought that was kind of interesting to know about. But moving forward, if I want to take this California image and just see the pixel values themselves all together, you can actually like read them in as like an array, and it'll just show you all the values for the colors. So this is that. This is the actual picture that I just read in. And so it's just me saying, hey, show the image of California on map. This is just a size 10 by 10 plot.show. Just show me what it looks like. And now I decided to change the X and Y coordinates to longitude and latitude, just because I really wanted to take advantage of the fact that we had that data. I thought it was kind of interesting. So this is just me changing some of the longitude and latitude coordinates. And so now I believe I just overlaid the plot that we saw previously on top of the California plot to literally see where in California these houses were like being plotted. And so we see literally like on the more coastal regions, we have like the most expensive like population of the houses, and more inland, we see that it's like significantly cheaper for whatever reason. To myself, I kind of thought like, why would that be? Certainly because they're not on the coast of the state, but you know, it's I guess something to think about. You know, houses that are more inland are generally speaking less expensive. So if you are someone who wants to move to the West Coast, maybe that's something to consider.
What are the take them?
Yeah, definitely right here. Definitely right here. And like maybe like right here.
Some parts of California, just like desert.
Yeah, literally.
Forests and
Yeah,
stuff
I was
there.
thinking like maybe it's like forest fire or like
Yeah, more than-
region. Yeah. So I was like, I didn't know if that had anything to do with the implication of the price, but certainly there's a lot of room for conjecture and like reasoning between that. So I'll leave it.
Like the house prices, it's only
Yeah.
lakes that
Yeah. So right here, it's not really like significantly more expensive. And right here, it isn't either, which is kind of interesting, I guess, to look into maybe.
I guess in California, lakefront properties aren't worth that much, but
Yeah, it's all about Laguna Beach.
yeah. Because you can
Yeah.
get a map that was annotated.
I was trying to do that. It took some time and it didn't work the best, but
The map is about Karnataka whole different.
yeah, it really is. Like I was trying to just get this like plot to fix. I thought it'd be like pretty, it'd be like a little more interesting than like the average plot, but this alone took some like mind bending. So, you know, that could be an assignment for you. Maybe you want to do some real estate analysis and then you'll figure out how to use GIS and geographic plotting to figure out where to place the cities.
In real estate, there's a lot of money.
Yeah, there's a lot of money, so it'll incentivize your quest.
Yeah, so, if we, would we be able to, let's say, have the app like this, different ways, and have the, have somebody figure out whether you're close to the ocean or not, let's say if you didn't have the ocean?
I mean,
I'm not, wait,
have
can
the
you ask that
data.
again? Like,
We have the data already, so I think it's coming off that. He's basically asking to see, once you're in the superimposition,
Mhm.
to identify how far away the oceans are.
oh,
I think
Yeah.
you just treat the distance from ocean as your target variable and you will tell that they should go.
yeah. There's definitely ways to do that too, in a more like regimented way.
You should keep this data set for when you do like regression classification.
Yeah.
Activate it.
Yeah.
Show what predicted value.
I was gonna say that. I was gonna say that later. Like we can for the following meetings, next Thursday, the week afterward, we can either, implement a new data set. Well, maybe not next Thursday because it's when Travis gives us his data for air autonomy. But moving forward, we can look back on these data sets that we use here. It doesn't have to be a one-time thing. We can run different algorithms, whether it's classification, whether it's like regression, trying to predict the prices of things. So then you'll get like a more comprehensive experience with the data set. You'll know the features already. So it's not like each week you're switching new features and you have to learn new things about the data set. So that is something I was going to mention, but it's okay. We got that out. So yeah, back to this topic of ocean proximity, because obviously it's like a really hot item of interest with respect to this data set. And in terms of the pricing of the houses, I wanted to look into it. So I decided to call prox like this. I wanted to see all the unique values inside this column, right? And I wanted to call it prox because I wanted to get like just a quick and clear way to just constantly recall it. And so I did that. I assigned the ocean proximity's unique values to prox. And now every time I call prox, I will get an array that tells me all the values. Again, this is near the bay. This, I believe it was less than 1 hour away from the ocean. This is inland. This is near the ocean. And then this is island. And so I wanted to see what houses, okay, I want to specify the houses near the ocean location that pop up on our map. And so I decided to take 3, which is near ocean. So 0, 1, 2, 3. And I assigned that to a certain like variable. And now I created a plot using that. And basically in this plot, I'm isolating specifically for just the houses that appear on the coastal region. There's ways to identify for a lot of different things, but this is how I decided to choose for this. And as we just continue, you can just like specify for different values. In this case, 1 corresponds to less than 1 hour away from the ocean. And so that's right here. I decided to reassign it to ocean with the proximity of 1. And now these are all the houses less than 1 hour away from the ocean. So we see like, you can literally see like, depending on where these houses are in California, the state, you can see how the pricing changes with respect to each ocean proximity metric. So now I want to use Seaborn to do some like further data analysis. I thought it'd be a little interesting to do. And so moving forward, of course, I want to see the head of this data set. And so I decided to take some more information on the median income this time. I wanted to look into this bins. And so this is how it breaks out. And so I tried to use something called the quantile cut because I wanted to kind of like take an approach to this data set where it's like, okay, like because the income is such a big deal with predicting like the overall price of a house, then we can kind of like split the income into different bins and kind of like see if we can like take a quick classification depending on like where your income range lands, like what housing you'll be able to like purchase. So that's what I decided to do. So Q-cut is like this quick method that actually it means quantile cut. What I did was I created different quantiles. 0, 25, 0.5, 0.75. I also took 0.95 and then just like 1. And so this is literally telling me like in these different splits, I have from the values of this range to this range. I have the values of this range to that range, inclusive. And so this is just telling me like the different values that can be found in these quantiles. Moving forward, I did something called bin discretization. It just means that we turn numerical variables into categorical variables. That's like the English translation of that. And so again, I decided to take the income category. I did this quick cut of the quantiles, and I now gave them new names and labels. So now we're saying, hey, there's gonna be a low. So these meaning the income range is gonna be low, below average, above average, high, and like very high. So moving forward, this is just the breakdown of the relative counts of the percentage of houses in these categories. So there's houses that correspond to, this above average. These are the percentage of houses in this range, low average, the low segment. The below average segment corresponds to about 25%, high is about 20%, and very high is like 5%. It's a very small amount. And this was something that I just quickly created, a featured engineered column. So this is me taking a quick look at it with respect to this quantile cut that I just created. And so moving forward, I just want to take a plot and see, okay, if we're going to look into ocean proximity and the income category with respect to this data set that we've been using the entire time, we want to use this color palette. I'll have to change the colors. This time it's called Inferno. We can just take a quick look at the count of the different houses with respect to the income category. So this is what it broke down into. Very high, of course, is like a very small amount of the houses. Low corresponds, there's a lot of values in low. And also, if you look into it, there's going to be like nearby, like you can see with respect to the proximity of the ocean on the state of California, you can see, okay, this is in the above average category, the amount of houses are less than 1 hour away from the ocean. Like it breaks it down into each, into the distance it is from the ocean. So this is just another way to approach that. This is me taking this and breaking median housing values and the income category into bins. And by the way, this black line, it actually corresponds to a confidence interval. It means that we're 95% sure that the housing value is like between this range. And so that's just what that corresponds to. I was curious when I saw that myself, so I did some digging, and that's what that means. And now moving forward, I decided to use ocean proximity and median housing value this time instead. And so now we have a different breakdown. You guys can feel free to ask questions, of course. So again, ocean proximity, I want to see the different value counts. And I noticed that island has like literally like 5 instances. So I just like got rid of it. I was like, that's like so small that it's like, in this case, not a big item of interest. And the reason why I was doing this was because I wanted to create like a heat map. It's one of my favorite things to do because I think it has like a really good way to represent information in like a matrix format. And so I did a group by, which we did in one of our first meetings on these 2 categories. I took the median housing value, I took the mean of that, I unstacked the data, and then I dropped this. So again, it's called method chaining. It means that you're using like multiple methods. It's almost like sub-selecting what you want by adding continued like methods after some call that you're having. And so I store this in matrix. I turn this matrix into integer values. And ladies and gentlemen, I created a little heat map that tells us the income category with respect to ocean proximity. And we can kind of see, okay, like the literal counts of like the prices of houses, or not the prices of houses, like the income category for the houses. We see that there's certainly like more expensive houses closer to the ocean, like we've been discussing this entire time. So this isn't like too big of a surprise with our data, but it's something to see. And then we're actually towards the end. I thought I'd run out of time. So okay, yeah. So one thing I will hasten to mention is that I didn't want to run some machine learning algorithms on this, but I figured we probably wouldn't have enough time. And some people actually told me after, the first 2-3 meetings that they particularly liked the fact that, I actually put like practice problems in, after the first meeting. And it's a good way to, practice, get your understanding at a sharper point, and even just get general practice. The more you practice, the more you can remember these things as you're going through new data sets. So I can actually make like a quick practice notebook and like put it in to the group chat. And then of course I can put in the solutions into group chat so you guys can also see.
Really bad data.
Yeah.
Yeah.
Or I can be nice and give you nice data, but
You're leading into exploratory data analysis.
yeah. So I'm gonna, we can
Nightmare data sets.
yeah. We're almost done anyway, so it's good. But generally speaking, from now on, I'll try to give you guys some more extra practice and we can talk about it. If you maybe have extra time at the end of on a Friday and you just want to talk about the notebooks that were presented, we can even talk about that then if you don't have any homework assignments you want to go into. So these are just like items of interest that I just want to like air out so we can become a little more dynamic with how we practice, how we work with data sets, and yeah. So more feature engineering, of course, it's the name of the game today. This is, if I was going to do a machine learning algorithm, I want to create like a final label so that we can actually predict some of these prices or predict which region these prices would be in. I would take it out of the data set itself, like I would take out this final label from the data set just to make sure that we don't have it when we're predicting it. And yeah, just looking at some information based on this features column. We're taking, so because numerical values have like a bunch of different scales, I just turn these feature types into a float. And lastly, this is the SciPy like logo. There's some scientific computing stuff you can do with like just some standard statistics, like z-scores, standard deviation, like you can run a bunch of different things on your data. And so,
Your Zoom stop off the screen.
oh, it's fantastic. Just like the other day.
Maybe just reshare the screen.
Yeah, yeah. You know what? We can just stop here. Yeah. All right. Well, I'm sure you guys learned all you wanted to learn today.